Hello and welcome to this clip, which is designed to help you self-check and self-analyze your review organic exam questions that I've set you. This should help in your preparation for both the practice exams during mock week and also in possibly the end of year progression test as well, because it covers several different topics. So please make sure you've actually completed the homework and tried to improve your answers first before using this clip. It'll be more valuable if you've had to think about your answers initially before just going straight to watching the clip and not really thinking about why your answers were wrong. Try to correct them first and then come to this clip and use it to fine-tune some of your answers you weren't able to improve yourself. So the first part of this is looking at basic organic chemistry. So this would need you to go back over your notes from basic organic chemistry and look at the different types of reactions that you might come across. So you've got free radical substitution, electrophilic addition and elimination. So the key words there are the substitution, addition and elimination parts. And that will help you decide what kind of reaction you're looking for. So it might be worth grabbing your flashcard definitions of substitution, addition and elimination reactions before you go any further. So you can pause the clip now if you wish before resuming. So the thing to do is to look for the functional group changes as well. So starting with free radical substitution, if you look at the selection of reactions you've got, hopefully you'll remember that free radical substitution occurs in alkanes and also involves the use of UV light to create homolytic fission. So that would obviously be reaction 1. The second one, electrophilic addition, an addition reaction means two things coming together to make one product. And also electrophilic addition only happens at A level with alkenes, so it's obviously going to be something that is involving an alkene. So if you look at the reaction sequence, you can see clearly that compound C is an alkene because it's got a carbon-carbon double bond. So that must mean that reaction 4 is your electrophilic addition. And finally, elimination is when a small molecule of some kind is eliminated or removed from a larger molecule during the course of a reaction. So that would require something to be split up in some way, some larger molecule to be split up in some way. So if we look at reaction 3, you'll see that there's the formation of a carbon-carbon double bond when there were no carbon-carbon double bonds before. There's a carbon-carbon double bond here, so hopefully by highlighting those two bits of the reaction scheme you can see that the carbon-carbon bond created in C must have meant that something was removed or eliminated from A to create the need for a carbon-carbon double bond to be made in the first place. So that must mean that reaction 3 is our elimination. So if you move the page down so we can see the remainder of the questions. It says, in reaction 2, the aqueous OH- ion acts as a nucleophile. It says, state what is meant by the term nucleophile. So I'm going to put this in the 2015 specification requirements. So it's a species which donates a lone pair of electrons to form a dative covalent bond. The next part asks us to do a mechanism. So it says the mechanism involved in reaction 2, so we've got to look back at reaction 2 in a second. So going back up the page to reaction 2, you can see it's the substitution of an OH for a Cl. So I've just highlighted the functional groups there. So we've now got to think about what has to happen for the Cl to come on and the OH to come on and the Cl to come off. So the first thing I do is add my lone pairs and my dipoles. So my lone pairs tell me where the curly arrow starts and the dipoles will suggest where it finishes. So I've got two electrons on my oxygen. What's going to happen is they're going to move towards an area of electron deficiency to form that dative covalent bond. So that's your delta positive carbon. So remember, your lone pairs should be the start of your curly arrow, or you can start them at a bond such as the breaking of the CCl bond in that mechanism, and they have to finish on an atom. Now obviously if something is being substituted, then something else has to come off the molecule. So don't forget that chloride has to come off. It's now a chlorine atom, but it becomes a chloride ion. So you can put that in as your missing other product. So then it says compounds B and D are structural isomers of each other. Now it doesn't ask you to look at B and D again, it just states that they are, but then it asks you to explain what the meaning of the term structural isomer actually is. So this is straight out of your flashcards, compounds with the same molecular formula but different structural formulae. Okay, so let's go on to the next page now. Okay, so let's have a look at the next page. What I've done on the next page is I've transferred a couple of the structures over because it's still asking about compound B and D. So it's asking you to draw the skeletal formula of B and D. Obviously you can look at the previous page on your script to double check this. So there's obviously more than one way to draw these skeletal formulae. What you've got to check is, do you have the right number of carbons and do you represent the carbon-oxygen bond correctly? For example, the one on the left, I've highlighted the 3 carbons and you can see them on the displayed form for the structural formula as well. And you can see the similar arrangement for compound D too. So it says compound C can be polymerized to form compound E, and it asks you to state the type of polymerization. So if we put in compound C, we can now think about how it's going to be polymerized. So it's got a carbon-carbon double bond, so that means it's addition polymerization because you add across the carbon-carbon double bond to create the monomer unit. Or sorry, should I say the repeating unit. So what you've got there is your monomer. So the answer would be addition polymerization, and the name of the compound would be compound E. So if I move the page down, and it asks us to draw a section of compound E and showing 2 repeat units. So how would we identify one repeat unit out of those 2, just so you know that you're doing 2 of the same thing? So the blue shaded area will be 1 repeat unit. So the main thing to also remember is to not forget the trailing bonds. That's essential. If you don't have the trailing bonds in there, you won't get the marks at all for this. So let's move it down to question 2. So it says cyclohexane can be converted into cyclohexene via a 3-stage synthesis. And in the first stage, cyclohexane reacts with chlorine to form the organic product compound A. So how do we work out what compound A is? So if we remember that cyclohexane is still an alkane, like a straight chain alkane, in the sense that it's not another type of functional group, it's just carbon-carbon single bonds but joined up in a ring structure, it's still only going to undergo free radical substitution with a halogen. So therefore, what's going to happen is that you're going to get a substitution of a chlorine onto the cyclohexane ring, a little bit like that. Okay, so let's go to the next page. So I'm assuming here you still have your previous page that you can go back and have a look at. So stage 3 involves the dehydration of an alcohol, and it asks you to state a suitable reagent for dehydrating an alcohol. Now there's several different options here. In the textbook at A level they generally talk about H3PO4. So you're looking at concentrated H3PO4 or concentrated H2SO4. I think it's really important to say concentrated here, because if you say dilute, the alcohol won't be dehydrated because the acid won't be strong enough. And it asks you for a suitable balanced equation for the dehydration of cyclohexanol. So it's quite important here to look at what they've actually given you. They've given you cyclohexanol, and they've given you a structural formula for it as well. So if you were to write it out in a skeletal form like that, you'd make sure that the carbon-carbon double bond in your cyclohexene is next to where the OH was situated. So the 2 possible places it should be are now highlighted in blue. Obviously you could also use C6H11OH to write out your equation as well. So you could put it in like that as well. Don't forget though that you should really keep the OH as part of your formula on the left, as opposed to doing C6H12O, just to make sure that the examiner knows that you are aware of the functional group changes. So it says that the reaction in stage 1 is quite difficult to control. And it gives you one other possible chlorinated product as 1,4-dichlorohexane. So then it says 1,4-dichlorohexane reacts in the same way as compound A in stages 2 and 3. So then it says suggest the structure of compound B. Now if you look at the original reaction scheme, you'll see that there was one chlorine on the second compound along, so it was chlorocyclohexane. Here there's two chlorines, so all that's going to happen really is the same thing's going to happen twice. So you're going to get a diol, like that structure there, so that's what they're after. You could also argue that you'd only get one of the chlorines turn into an alcohol, so it could only go part of the way. So technically that could be a legitimate possible product as well, if you only had a partial reaction. Then it says two cyclic alkenes C and D are formed in stage 3. And they're structural isomers, so it asks you to suggest the structure. So from this first structure, when you have a diol, you could have three possible options. If you have a chlorinated alcohol, such as the one on the right hand side of the screen in the middle, you could have the structure on the right hand side box. Okay, so you can probably see at the bottom of the screen that it's ended that question, so let's go on to question number 3 now. So this question asks you about 2-chlorobutane, and it tells you that it reacts with OH- in aqueous conditions to produce alcohol A. And it asks you to identify alcohol A. So they're looking for buton 2-ol, or some suitable formula representation of this compound, like skeletal or displayed, or a mixture of the two perhaps. But then it goes on to ask you to describe the movement of the electrons in the mechanism of this reaction. So obviously it's going to be a nucleophilic substitution, because OH- is a nucleophile, and the chlorine that comes off the butane and is replaced with the OH- is also a nucleophile. So one nucleophile is being swapped for another. So it's a nucleophilic substitution. So I might as well point out at this stage, it doesn't necessarily have to be one nucleophile swapping for another. It generally works out that way. It doesn't have to be by definition. It could simply be that an atom or group of atoms substitutes for another atom or group of atoms for it to count as a substitution. But for it to be nucleophilic substitution, the group that attacks initially, so in this case the OH- coming and attacking the 2-chlorobutane, the attacking group has to be a nucleophile. So there's 5 marks on offer. So the first thing I normally do is I put in my dipoles. I'm going to switch to another colour to make this a little bit clearer. So next I put in my nucleophile, OH-. I need to put my minus charge in. So I start my curly arrow between the electrons in a lone pair, and I point it at the carbon that's delta positive, and it has to touch that atom. Then the curly arrow comes off the carbon-chlorine bond and points directly at the chlorine atom that is partially negatively charged, the delta minus Cl. And finally I put in my products, both of them, my alcohol and the chloride ion. So let's move it down so we can have a look at question number 4. So it's a similar kind of question, isn't it? It's asking you to do the same thing, but this time they're calling it hydrolysis, because it's hydrolyzed with hot aqueous alkali. The 1-chlorobutane this time, but it's the same nucleophile as OH-, so it's the same thing again. So first of all, put in your dipoles, and start your curly arrow between the electrons and the lone pair and the oxygen, and point it directly at the carbon that has delta plus charge, and then the bond between the carbon and the chlorine breaks heterolytically, and the curly arrow starts at the bond and points at and touches the chlorine. So obviously the other product is Cl-. So let's move the page down a little bit. We're finished with that page, so let's go to the next one. This time they're talking about another halogen alkane, or haloalkane, has an MR of 127, has the following composition by mass. So you need to show that the empirical formula of compound H is C2H4Cl. So it's quite straightforward what you do here. So you take each percentage and divide it by the relative atomic mass of that element. So it gives us those numbers, and now what you do is you divide by the smallest. So that gives us a ratio of 2 to 4 to 1, and therefore that gives us the empirical formula. So to work out the molecular formula, you need to work out how many times 127 goes into the empirical mass, or what the theoretical mass of C2H4Cl would be. So therefore the total of that would be 63.5. So therefore the molecular formula is the empirical formula multiplied twice. So it's C4H8Cl2. So then it asks us to draw the structure of butane 1,3-diol. That's just simple knowledge and recall of how to draw out alcohols. So that would give us that kind of structure. It doesn't matter where on carbon 1 or carbon 3 you put your OH. It can be on top or on the bottom or at the side, provided it's on carbon 1 and carbon 3. Then they want the structure of compound H. Now compound H has 2 chlorines in it, and therefore if the C-Cl bond is hydrolyzed with the OH group, then it's going to replace the Cl onto that bond. So therefore, working backwards from that idea, you would have started with the structure I've just drawn, but instead of OH, have Cl on each position. So you have something looking like that. Okay, so let's move on to question number 5. So here it says halogenoalkanes or haloalkanes are used in the production of pharmaceuticals, polymers, and flame retardants. And it gives you one example, a slightly more complex sounding one here, 1-bromo-2-methyl-propane, so a branched bromoalkane. And it's used in the production of ibuprofen, painkiller, and can be prepared from reaction between 2-methylpropan, 1-ol, and HBr. This time it's a calculation one. It's a bit more mathsy, so it's asking you to work out the number of moles of your 2-methylpropan 1-ol that was actually used. So the first thing you always do is quote the MR clearly and signpost it. Don't just stick the number in there somewhere and hope to get the mark for it. Actually put it in there like I've just done. So now you calculate the number of moles using moles equals mass over MR. So the mass of your 2-methylpropan 1-ol is 4.44 grams. So your 4.44 gets divided by 74.0, and that gives you 0.06. So then it asks you to calculate the number of moles of 1-bromo-2-methyl-propane collected. And again, they've given you the MR. This time they've done you a bit of a favour. So it's only 1 mark here because you don't have to calculate the MR. They give it to you, so that's why it's 1 mark for this and 2 marks for the other one. So here we're straight into moles equals mass over MR. So you lay your working out like that, and that gives you 0.04. So then it asks us to calculate the percentage yield. So we need to move the screen down so we can do that. And it also asks us to quote our answer to 3 significant figures. So you don't just calculate the percentage yield, but you also do it to 3 significant figures, all for your 1 mark. So if you miss one of those 2 things out, you won't get the mark as a sort of consolation prize, for want of a better way of describing it. They won't give it to you. So let's get everything that we need put in. So our calculation should be based around that idea. So the actual moles that we got was 0.04, and the theoretical moles, because it's a 1-to-1 mole ratio, should be 0.06. So just to confirm that, if we go back to the top of the page, you can see it's a 1-to-1 mole ratio. So therefore, we need 0.04 over 0.06 times 100. So that's 66.7%, not your calculated value of 66.6666667. It's 66.7% because they want 3 significant figures. Right, okay, so let's see what the next question brings. So this one says trifluorochloromethane is an example of a chlorofluorocarbon that was commonly used as a propellant in aerosols. So it asks you to draw the shape of a molecule. So show this shape. So what that doesn't mean is simply draw the displayed formula. You must show the three-dimensional shape. So it's carbon with 4 different atoms coming off it, so that's 4 areas of electron density, so therefore it's a tetrahedron. Tetrahedron must be drawn with that type of orientation. Straight line up, straight line down, dotted line right, wedge left. The wedge can be on the right, the dotted line can be on the left. So now we can put in the 3 fluorines and the chlorine. It doesn't really matter where each one goes, provided we end up with a tetrahedral shape. So just to clarify, the exact placement of the 3 fluorines and the chlorine atom is unimportant, provided you have a 3D representation to get that mark. So an approximate bond angle, going back to your idea of shape, would be 109.5 degrees. Then it asks you to suggest a property that makes that compound suitable as a propellant in an aerosol. Now, a propellant is going to help to propel the droplets out of the aerosol can into the air. So it's going to need to be volatile or have a low melting point. It also needs to be non-flammable or non-toxic, unreactive, so lots and lots of different things you could possibly say. Now, all of these are just simply a bit of common sense. You don't have to know anything particular about fluorochloroalkanes, literally just that for a propellant to work, it needs to not interact with the material you're trying to propel. So let's say it was a deodorant can. You don't want the propellant reacting with the deodorant as you spray it into your armpit. That wouldn't be very nice. You'd be quite sore, I would imagine. So we want it to actually just sit there, do its job, help propel the material inside the can and nothing else, and not put you at risk. Okay, then the next part, when chlorofluorocarbons are exposed to strong UV radiation in the upper atmosphere, you get homolytic fission taking place. So you've got to explain now what homolytic fission actually is. But you need to be quite specific about how you say it. So I'd say the breaking of a covalent bond where one bonding electron goes to each of the 2 bonded atoms. Because you can see there quite clearly it's 2 marks that's on offer. So it's not just knock something out that kind of sounds right. It actually means go and look it up and make sure that it is close, or if not identical, to the definition in the textbook. Okay, so let's now move this page down a little bit so we can see the next question. So then it says, suggest which bond is most likely to be broken when CF3Cl is exposed to ultraviolet radiation. So thinking about it, you've got CF bonds and you've got a CCl bond. And if you remember, the rate of hydrolysis work that you've been doing on haloalkanes would suggest that as the bond enthalpy increases, you're going further up the group of the halogens. So CF bonds are stronger, should we say, than CCl bonds. And the reason, like we just suggested, is you have a lower bond enthalpy. Notice how I've sort of made reference to bond enthalpy by putting it in bold. I'd say that's the most precise thing to talk about. You could say lower bond strength, but let's stick to the terminology we've been teaching you. So lower bond enthalpy is what I'd recommend as a slightly better way of saying it this time. So, if you break that CCl bond, what 2 things are you going to get? So you need to draw your 2 radicals. One of them will be a Cl dot, one will be a CF3. So something along those lines would be fine. Okay, so let's now look at the next question. So we're now into some alcohols work. So it talks about butan-1-ol being oxidized to form butanol. So the oxidizing mixture would be a bare minimum of dichromate ions and acid. So instead of going into all the different ways in which you could say those 2 things, I've just left it to you to decide whether your answer is acceptable. So Cr2O7 2-, so you'd have to have some reference to dichromate and also some reference to acidification. You'll notice it's 2 marks, so 1 mark for each of those things. The colour change has to be quite specific. As you've seen in class, it's from orange to green. It's also in your textbook and on the clips you've watched to prepare for your teaching. And then it's into a bit of spectroscopy, so you might want to have your data sheet handy here. I'm not going to bring the data sheet up on the screen here, but if you have yours handy, it'll be useful to cross-reference while you're watching. So then it says a sample of butanal from A was analysed, so not the butanol, the butanal, so the aldehyde, and the infrared spectrum contained an absorption in the region 1680 to 1750, but did not contain a broad absorption in the region 2500 to 3300. Now the absorption in the region 1680 to 1750 centimetres to the -1 would be your C double bond O in the aldehyde or ketone. Now notice I've been specific not to inadvertently say the C double bond O in a carboxylic acid. That's because it said that it didn't contain a broad absorption in the region 2500 to 3300. So be careful not to inadvertently step aside from the correct way of putting it. Now if you think about a carboxylic acid, you've got a C double bond O in there somewhere, so you would have 1680 to 1750, but you would not have 2500 to 3300 in this case, so that must mean it's not a carboxylic acid. Which brings us on to the next answer. So it doesn't contain an OH group as part of a carboxylic acid or carboxyl group. So bringing the page down to see the next part. So the reaction in A was carried out using distillation and not reflux. And the reason is because we want to get the aldehyde. So we want the aldehyde to be separated out, otherwise you'd end up getting the carboxylic acid instead. You get the full oxidation. So the next question talks about a compound you won't have come across before. This will be an example of an applied question. So citronellol occurs in both rose and geranium oils, and it wants the two functional groups. So remember we've talked about carbon-carbon double bonds being the functional group, as well as functional groups that have other new atoms in them, such as oxygen or chlorine. So you've got a C double bond C, or alkene, and you've got an OH group in the form of a primary alcohol. So notice I've put the words and the actual the atoms in as well, just to cover myself. So the next question moves on to spectroscopy. So the functional groups in citronellol, if you remember, they were C double bond and OH, could be identified either by chemical tests or by infrared spectroscopy. So it says state which of the two functional groups you named in A is identified when bromine is added to citronellol. Now it's bromine, so bromine undergoes electrophilic addition across the C double bond. So that's what we put in. And the one that's more easily identified from the infrared spectrum is the OH group. So in terms of what you'd see, I'd suggest that you'd say the bromine is decolorized. So if you wanted to say it went from orange to colorless, that's okay, but that's only assuming that there's not a lot of bromine that you've added. If you've added a lot of bromine and all the citronellol reacts and then there's some bromine left over, it's not going to go to colorless. So if the bromine is in excess, it's not going to go to colorless. But decolorized covers you for all the eventualities. So if you're going to go and remember something, put it on a flashcard, I would say decolorized. So the next part is to put the skeletal formula of the organic product formed. So you add two bromine atoms across where the double bond used to be. I haven't left myself much room, so my second bromine sticks out at a slight angle there. That's not technically okay, really, but given the circumstances, hopefully you'll forgive me for that minor indiscretion. Then we've got the infrared spectrum of citronellol. And it asks you to mark on the spectrum with the letter X the absorption that confirms the presence of the functional group that is most easily identified from the spectrum. Now we just decided that it was the OH group, so I put your X over just beyond 3000, somewhere like there. Then it says the reaction of a sample of citronellol with hydrogen in the presence of a catalyst results in the formation of a saturated compound C. So it's a bit saturated, that means the carbon-carbon double bond has been hydrogenated. So this is normally done using nickel. The one in your textbook mentions nickel. There are several others that you could use, several other transition metal elements, but nickel would be the one that I would suggest here. Okay, so let's make some more room on the screen to have a look at the rest of the question. And it says, determine the molecular formula of the saturated compound C. So I'm assuming that you've got the previous page with you. So just looking at the actual formula in skeletal form, we can quite easily work out what its molecular formula is. So that gives us C10H22O. So let's go to the next page. You can clearly see we're at the bottom of that particular page. So then they want a balanced equation for this reaction. So it was a hydrogenation. So hydrogen is one of the reactants. So remembering that it was hydrogenation means the addition of hydrogen across the carbon-carbon double bond. You have 2 hydrogen atoms more in your product that we've just worked out as C10H22O. So the original compound must have been C10H20O. So the next one is another example of an applied question, lavandulol, another weird and wonderful compound with lots of different things on it. So let's have a look at that one, shall we? Move the page up so we can see it a bit better. So the 2 functional groups are C double bond C and OH, but alcohol. So don't forget to say alcohol. And it says, why does lavandulol not have cis-trans isomerism? So if we look carefully at the carbon-carbon double bonds, on each carbon-carbon double bond, on one of the carbons, the 2 end groups are the same. If you ever see that, that means that that carbon-carbon double bond does not show cis-trans or EZ isomerism. So let's move the page down so we can see what the next part says. So then it says lavandulol also reacts with bromine to form a saturated organic product. State what you would see in this reaction. Again, it's bromine decolorizing. And then they want us to do the molecular formula. So I'm just going to bring the structural formula of lavandulol down again. So we'd have C10H18OBr4. So why in that particular order? It's because what we need to do is list the atoms that were there to start with, and then any newly added ones. So because the bromine, or the bromines, were added afterwards, the C10H18O, they were already there in the original lavandulol. So if you did Br4 and then O, you would lose a mark out of the 2 that are available, because it's just a little protocol you have to follow. So let's go to the next page. We're nearly there now. And it says lavandulol can be oxidized to produce either compound Y or compound Z. So bearing in mind that the original lavandulol has an OH group in the positions where you now see CHO and COOH, it says write a balanced equation for the oxidation of lavandulol to produce compound Z. Now remember, in the previous question we were asked to work out what the structural formula of lavandulol was, or the molecular formula. We can now go back to that and refer to it when working this out. Now remembering that carboxylic acids are only formed from full oxidation, not partial oxidation of an alcohol. It has to be 2O and H2O. So 1 mark is for saying 2O, 1 mark is for saying H2O. And it says an infrared spectrum of either compound Y or compound Z was obtained and contained absorption between 1680 to 1750. However, there was no broad absorption between 2500 to 3300. So going back to your data sheet, it's the same as the one earlier, isn't it? You're eliminating the OH from the carboxylic acid, in the sense that you're not taking the OH group out of a carboxylic acid group. You're saying that in the spectrum, because there was no broad absorption. I'll just pause for a second and I'll highlight the bit I'm trying to talk about, otherwise I'll get my words mixed up a little bit. Looking at that bit, that means that it cannot be a carboxylic acid because there's no OH as part of a COOH group. So if we're just left with 1680 to 1750 centimeters to the minus 1, that must mean it's compound Y. So there's 2 things you need to say quite succinctly here. The absorption at 1680 to 1750 centimeters to the minus 1 represents C double bond O, and the absence of a broad peak at 2500 to 3000 centimeters to the minus 1 indicates no COOH group. It's important both of those points are made. So I thought I'd put this one into the homework because it's to do with the experiment that you've done and you've seen demonstrated. So it gives you some data about the boiling points of ethanol, ethanal and ethanoic acid, and it's saying to use this table of boiling points. Let me bring the screen down a bit so you can see why the organic product is likely to be ethanol if the apparatus shown in figure 1 is used. So it's not just that you use distillation to get the aldehyde, you actually have to use the data. So you've got to be a little bit careful not to rush in here. So there's two ways you could come at this. You could talk about it in terms of the aldehyde being having a lower boiling point than the alcohol and the ethanol. You could also say that partial oxidation is ensured. Now, there's 2 marks here, so we also need to say something else. I would also recommend saying that volatile components can escape or be distilled out. So it's not just saying the boiling point is lower. So the more volatile aldehyde will be distilled first. So bringing the page further down so you can see what we're doing. So it says why the organic product is likely to be ethanoic acid if the apparatus shown in figure 2 is used. So let's look at figure 2. You can see that figure 2 is refluxing apparatus as opposed to distillation. So here what we need to say is volatile components can't escape, so complete oxidation is achieved. So those 2 points will get you the 2 marks in that one. Okay, so let's go on to the final part of the question. It asks us to write a balanced equation for the oxidation of ethanol to ethanoic acid and use O in square brackets to represent the oxidizing agent. So don't forget you have to have the correct number of O's and the correct number of H2O's. When I say O's, the correct number of O's in square brackets. So it's a double oxidation, once of the alcohol group to start with to an aldehyde, and then one more of the aldehyde through to COOH. So I think that takes us to the end of this homework. Hopefully this clip has helped you understand a little bit more how to construct your answers across a range of organic style and spectroscopy style questions. So finally, don't forget to clarify with one of us here at college any aspect of this which is unclear, so pop into a subject extension because we're here to help. So well done for making it to the end of this homework. It was several things you had to be able to get your head around all at once. But thank you for your time and your patience, and I'll see you soon.